So let me wait for a few minutes if anybody joins, then we can start.
Okay,
So how are you doing right now?
I was revising the lectures of the previous courses of statistical mechanics.
So you are now in third year?
Yes, after the exam of fourth semester, I will be in third year.
In third year.
I was feeling tough from the week one lectures, like the postulates.
This week lectures.
Yes,
No, actually, he just that's right, actually. Okay, I will try because if you have gone through the lectures, then you can see there is only discussion and the historical development. These things are discussed. So eventually, I have to discuss some theoretical things only. I have to discuss. No mathematical question I have to discuss today because I have to discuss only. I will discuss in detail some parts I have thought about the random variable part are discussed, but not in detail. So I will discuss that part, random variable part, and also I'll discuss that ergodic hypothesis and ensemble average or this time average, how they can be treated equally. These things we'll discuss today, and few questions as well from that statistical part, stochastic part. That things I will discuss. I plan that. Let's see what happens. And if you have any specific doubt regarding the this week lectures, then you can ask me. Then I can understand because this week lecture maybe feel like some scattered way, right? It's some, but it's okay because it's just a
the first part of the postulate was tough. Time average equal to
time
ensemble
ever.
average.
That I will discuss. Good. That's the main thing of the statistical mechanics. You can say that's the
Which ensemble was that?
no. That is not any specific ensemble. That's a general description. You can think like any of the ensemble, but that classification came later, na, that whether that will be canonical, microcanonical, grand canonical, that thing will came later, come later. But these discussions was very general. This was totally formulated by Gibbs. If he did not consider this ensemble average, the statistical mechanics would not have been developed even, because if you want to consider or calculate the time average, it's not possible. It's not possible to calculate any property, means entropy, enthalpy, internal energy, nothing. You can't calculate. You have to consider the ensemble average. Until now, we are calculating everything based on the ensemble average. That part I will discuss obviously, and also the stochastic, the random variable part. These two things will I will discuss today. So let me first connect my. So already five. So now we can start. Okay, give me some minutes. Let me connect my tab. I'm sharing my screen. So is this visible?
Yes.
Okay, my headphone irritates me, so I have to connect it again and again. So I have nothing to do with that. Uh,
Okay.
It's that you have. Let me start with the first question. Not question, it may be a discussion like this. What is the basic difference if you if anybody asks you what is the basic difference between the thermodynamics means classical or traditional thermodynamics and the first, what is the
Individual molecular property and bulk thermodynamic property.
exactly it it often called classical thermodynamics or you can call it as traditional thermodynamics. This is very important topic of discussion because uh, till now you have studied the traditional thermodynamics or little bit of statistical thermodynamics, but what is the major difference? Traditional thermodynamics was developed way earlier. It's in 80s, 70s, because the steam engine. Steam engine was the first, you can say the output of our traditional
I'm not
thermodynamics,
saying
scientific output. You can think like that. Uh, but statistical mechanics come very later, after you can say uh, quantum mechanics, after formulation of quantum mechanics, you can say that statistical thermodynamics or contemporary period, both, because Boltzmann and Maxwell, they provided some idea that is statistical mechanics, not statistical thermodynamics. There is some difference between statistical mechanics and thermodynamics. What is that? In statistical mechanics means in statistical mechanics we will deal with only the mechanics. Mechanics means force, how the molecules are distributed. These things we will discuss. And statistical thermodynamics means by using those information of that molecule, that means using the information of statistical mechanics, if you want to compute or calculate the thermodynamic properties of a system, then that is the statistical thermodynamics. So you can say the statistical thermodynamics is based on statistical mechanics of molecules, but it's not only that, it's beyond statistical mechanics. Okay, it's an application of statistical mechanics in to compute thermodynamical properties. That is statistical thermodynamics. But in our traditional thermodynamics, we basically deal with these things. We basically deal with the averages, right? Not averages, just the let's say just give me an example. Let's say it's visible, right?
yes.
Okay. So let's say if you have uh, gas, a chamber of gas like this, then this chamber of gas has several various properties. Okay, like temperature, pressure, volume, later internal energy, enthalpy, entropy. These are all our thermodynamic properties. This you can calculate. But if you see, let's say instead of I'm saying here it is an oxygen gas. Now everything is fixed, the temperature, volume, everything is fixed. Then if instead of oxygen gas, you are measuring this property. properties for oxygen gas. You are measuring temperature, you are measuring pressure, volume, everything. Now I'm changing this gas from oxygen to, let's say, carbon dioxide. So if you see from a thermodynamical point of view, these properties will not be changed. You will have the same value of temperature, pressure, volume, everything will be same. That means basically thermodynamics never
Internal
deviate.
energy will be different.
What?
Internal energy will be different
Why?
because
What is the
it's
formula of internal energy?
ra-
3 kBT,
there
right?
you tell me
So why it will be different? 3 or 3 by 2? 3 by
3
2
by 2.
kBT. 3 by 2 kBT. So why it will be different? If it is oxygen or
Oxygen
carbon
is
dioxide?
diatomic, CO2 is triatomic.
No, no, no. That you know the statistical description later. Without knowing statistical description, you can't say that. These things you have to separate. That's why this is historical development is important. So when you are adding the rotational or vibrational these things, then you can differentiate between oxygen and carbon dioxide. That's why now, when you in considering the rotational or vibrational things that don't want to talk right now, but still, uh, then you are focusing on the structural orientation of that particular molecule. Then only you can figure out. Otherwise, if you only consider the translation motion, every oxygen or carbon dioxide, any molecule will be treated like a hard sphere, hard ball. That was also considered by Maxwell, right? What they have, if you see the derivation of Maxwell kinetic equation, there Maxwell clearly treated that all the molecules are considered as a sphere, spherical ball, right? And not only that, they are not interacting. They are not interacting, and also they are not occupying any volume of the container. These are the assumptions. Based on those assumptions, he had developed the kinetic theory of gases, and that is very successful theory because from that uh, theory you can essentially get the PV equal to nRT formula. So if you see in classical thermodynamics, you never differentiate between oxygen gas or carbon dioxide gas. All will give the same thing. So that's why
Your screen
thermodynamics.
was gone.
Huh?
Your screen was gone, so I cannot hear properly the previous
My
words.
screen was.
Gone. Network was not
Oh,
connected.
okay. Now you can see.
Yes.
Okay. Probably because outside weather is not very good actually. So it's heavily raining. So that's why probably network is interrupting. Okay. If there is a network issue, please inform me. Then I will fix it. Probably it's okay right now.
Yes.
Okay. Okay. Not bother with the orientation of molecule, how big the molecule is, or how the interaction between molecule is going on. That things are not important. So that's why thermodynamics is a bulk approach, or you can say it's a universal approach. That's why means you are seeing that you are just looking whole this whole container, not individual molecules. You are not focusing on the individual molecule, how their molecules are moving, how they collide each other. These things you are not focusing in thermodynamics. That's why it's a bulk approach. Okay. So we are just capturing the physics in a bulk point of view overall. As a macroscopic system. That macroscopic means as a whole container you can think. Microscopic means when you focus in individual molecules, then that picture will be microscopic picture. So these things you know actually microscopic, this picture. And as this is a bulk approach, you can say it's a universal theory. Thermodynamics, there is no fast. You can prove the thermodynamics, right? There is no proof from first equation. Can't write down the laws of thermodynamics. What you have taught, that's are basically the laws of nature. Just humans have observed that and formulated in a mathematical equation. In terms of mathematical equation, that's the thermodynamic laws. Okay, so you can't prove that. That's why it's a universal theory also. Universal theory means it will not depend whether the molecules are oxygen, carbon dioxide, these things, or whether you are measuring in Earth or measuring in Mars or measuring in air somewhere else. So it's very general theory. Now, these things is okay, but there is some limitation of thermodynamics. What is the limitations? You can't calculate the absolute values. You can't calculate the absolute internal energy, absolute enthalpy, absolute entropy. These things you can't calculate. What you can calculate, you can only calculate the differences. Del U, del E, del V.
Change
That
between two process.
what? Repeat it.
Change between the two equilibrium process.
Exactly. Two different state, if you consider two different state, then you can calculate the difference between that thermodynamical properties. So why? And that should be now because you are not. How you can calculate the internal energy? Let's say any arbitrary property, internal energy. That's the thermodynamical property. You can't calculate. Why you can calculate? Because you are not focusing on individual uh, molecules or individual particles. How you can calculate? That is not possible. You are just seeing 10 to the power 23 molecules as a whole. So you will have a overall picture. That's the difference. Um, because it's now clear that if you focus only one molecule, then there will be quantum effects. There will be very different physics is there. But when you see 10 to the power 23 molecule as a whole, then obviously the overall physics is classical, macroscopic physics. So everything will be, every quantum features, every statistical features will be die out. So only bulk is, picture you will be seeing. So that's the reason. And now, what is statistical thermodynamics? Statistical thermodynamics now, if you want to calculate from the molecular point of view, then you have to consider the statistical distribution. Statistics, statistics means distribution of something. That's the statistic. Statistical mechanics means a distribution of here. If you see the any particle, then the distribution of that part from the distribution of that particle, you can calculate velocity, you can calculate momentum and position. These things, these are statistical mechanical property. And thermodynamics is now using these properties, using the statistical description. Now, if you want to calculate those thermodynamical property, then it is a statistical thermodynamics. That's the difference. Okay. Is it clear? So, difference between statistical, this is actually our traditional thermodynamics.
Statistical thermodynamics and non-equilibrium thermodynamics are same.
No, no. Statistical thermodynamics, no, this non-equilibrium and equilibrium thermodynamics is a different approach. If you have two macro state, like let's say this is one macro state with N1, V1, T1, and another macro state having N2, V2, T2. These macro states are basically equilibrium state. Any macro state you can observe that is a equilibrium state. Okay, so now that is equilibrium thermodynamics. So traditional thermodynamics can also be equilibrium, non-equilibrium. There is nothing with statistical. Equilibrium means these states are equilibrium states. It will not change with time. That is the equilibrium state. And non-equilibrium state means in between, when you are having these two equilibrium state, in this path, all the state you are having, that's an equilibrium state. But non-equilibrium state, when you deviate from equilibrium state, little bit deviation, that's a non-equilibrium. That state's a non-equilibrium state. That will vary, change with time. That is a non-equilibrium state. So now you can calculate the prop. Okay, one thing is there. Using statistical mechanics, you can only calculate the properties equilibrium thermodynamics, obviously, not non-equilibrium. Non-equilibrium thermodynamics, even we are not we very little about non-equilibrium thermodynamics. because it's very difficult. These things, everything you have studied till now in thermodynamics, that's all equilibrium thermodynamics. Never you have got the non-equilibrium thermodynamics. In Clausius-Clapeyron equation, not Clapeyron, Clausius inequality, there is a inequality, right? That inequality actually refers to non-equilibrium, and equality means equilibrium. So every equation you have studied with a equal sign, equality sign, that essentially refers to equilibrium thermodynamics. If there is a non-equal inequality, that means non-equilibrium thermodynamics. That's we are not interested to study. That's a very difficult thing. But now, whether it is equilibrium or non-equilibrium, if you want to calculate any property explicitly from molecular point of view, you have to consider the statistical approach. That's the statistical thermodynamics. So if it's clear,
Yes.
okay. So let me summarize. So what I have taught, that or some molecules, and you are just measuring different properties. It's lagging. It's lagging. Okay. It's no, we can't do that. There is a lag. Okay. So then, if you let's say if you want to calculate the internal energy, you. So how you can calculate internal energy? You don't you can't calculate from a traditional thermodynamics approach. So let me relate. Okay, how you can relate traditional thermodynamics and uh, our statistical thermodynamics. There is some discussion. Let me write. This is very good. Yes. Microstate, macrostate is clear, I think. Yeah. Now, statistical mechanics, when we'll study, essentially we'll study the classical version, not the quantum version. If you incorporate the quantum effects, then that will be again quantum statistical thermodynamics. That's very difficult. That probably will not be important. So
What
let
is the difference?
what is the difference in between classical and quantum? When you are, let's say, these are
Okay.
molecules, right? These are molecules. So if you consider this as classical molecule, classical particle, you these things is very I have seen that students are confused with this. Statistical thermodynamics does not mean the quantum thermodynamics. That's a different thing. Statistical thermodynamics means you are now looking, focusing on each and every molecule, and you are seeing a distribution. You want to study the statistical distribution of those molecules, and from those distribution, you want to calculate the behavior, the average ensemble or thermodynamical property you want to calculate. That is the statistical thing. Now, if you consider this molecule as a quantum particle, then it's important. Later we'll see if this particle you have considered a Maxwell-Boltzmann particle, then that is a classical thing. If you consider the particle as a Fermi particle or the bosonic particle, then that will be a quantum statistical approach. Okay, so this is macroscopic and microscopic. This is okay.
In statistical thermodynamics, the particles are classical.
Obviously, we generally consider classical particle. Okay. Statistical mechanics gives average value that I will come later. This now let's say if you want to calculate mm, two macrostate and microstate is clear, I think, right?
Yes.
Let me again explain because these things is very important. What is macrostate and what is microstate? Let's say you have a this, and it is N1, V1, T1. I'm considering in general way. This is a equilibrium state. Why it is equilibrium state? Because it is not changing with time. Clear? Now you are disturbing from outside. It will not change until you disturb. You are disturbing from outside. Probably you are giving some heat. You are doing some work like that. Or if it do some work, or if it rejects some heat, means if it interacts with surrounding, then it will change the equilibrium state. If it does not interact with surrounding, it will be always on N1, V1, and T1. Clear? That's the equilibrium state. So
Yes.
it's a equilibrium state here. Let's say N1, V1, T1. It will not be changed if it don't interact with the surrounding. If it interacts, then it change to, let's say, another state, N2, V2, T2. That's another macro state. So these states are called macro state, equilibrium state, but macro state. Why macro state? Because under this equilibrium state, macro state, you can have infinite micro state. This thing is important. Means this macro state will not change with time. This N1, V1, T1 will be same. But if time changes, the orientation of molecule will be changed. Okay, let's say after some time the orientation may be different, maybe like this. After some time orientation will again change. This is very common, you know. So orientation will be changed, but still N1, V1, T1 will be same. So these all possible orientation under a particular macro states are called microstates. So in under this macro state, you will have infinite number of microstate. This is the definition of macrostate micro. So it's called folder file relation. It's a folder, and in this folder you can have infinite number of files. And while changing the time, all files are generated. Because each and every this is very important concept. Later it will be important. So each and every time, all new microstate will be developed. This is the equilibrium state under a particular macro state. Now if you let interact the system with the surrounding, then it will change from one macro state to, let's say, another macro state. This is another macro state. It is, let's say, N2, D2, T2. Under this macro state also you will have infinite number of micro state. That is clear. So now this is the this thermodynamics you know. For this case, let's say internal energy was U1, and here internal energy is U2. So you can calculate this del U, right? This del U can calculate
Yes.
thermodynamically. So this I'm just saying how we can bridge between statistical thermodynamics and our traditional thermodynamics. This value you know. Now, by using statistical mechanics, now where statistical mechanics come? Statistical mechanics will to calculate what I have said here. Under this macro state, you can have infinite number of microstate. So each and every microstate is a distribution of particles. Each and every microstate. So you will have a infinite number of distribution in energy, because now we are focusing on internal energy. Each and every microstate there will be a different energy. So let's say E1, E2, E3, you will have different number of energy. So there is a statistical distribution of energy of microstate. So you have infinite microstate, and among those microstate you will have a infinite number of energies, internal energies. So from here it will be clear. So now microstate are changing with times. So these internal energies actually changing with time. So now if you just time average of those internal energies, let's say this internal, I'm doing internal energy here, E. E is the internal energy of a microstate at a particular time t. Okay. And you are changing the time dt from 0 to t. Okay. And now later you divided the whole total time when capital T tends to infinity, because it's a equilibrium state. It will not change. You have to consider an infinite time. Then you will essentially get the U1. That is the definition of U1. Is it clear? Or it better to
Can
write
you please explain?
it better to write E1. E1 and E2. Is it clear, or if you have any doubt, you can say.
Why it is written E1 and E2?
It's a different macro state. So internal energy will be changed. Let's say I'm giving some heat, D cross Q. Then internal energy will be changed, na? Because you know
Yes.
D equals to del Q plus that W. So internal energy will be changed. So that change I'm not focusing on this system right now. I am just focusing if you want to calculate this E1, then how you can calculate. In
This
thermodynamics,
E1 is
you
this
don't know
E1 is
E1, don't know E2. You only know daily. But now we are trying to calculate the E1. So how you can calculate E1? That I am saying.
this E1 is for macro state or micro state.
Macro state. That's why it's thermodynamical property. Each and every thermodynamical property you can calculate. That's a macroscopic quantity. Microscopic quantity you can't calculate. So how you can calculate? Because under this macro state, there will be infinite number of microstates, and those microstates are overall. This macro state is independent. If you change, let's say I'm not giving any dq right now. I am just I just have this macro state, and let's say you have 1 year. It will not be changed. If you don't interact with surrounding, it will not change. It will be E1, it will be N1, V1, T1, everything will be fixed. But this is the macroscopic thing that will not change. But each and every time, new microstate will be generated. Is it clear? Let's say in a room there is a four people. Okay, you have locked them for 1 day. It's clear that four people will be there. That will not be changed. That will be always true. But the distribution of those four people in a room, that will be always changed. It's correct.
Yes.
Now, let's say if you want to calculate a property of those room, that is the overall weight. Let's say, I'm just saying overall weight. That will not be changed with the time. That will be same. But how you can calculate those weight? You have to calculate each and every uh, weight or energy, whatever you want to calculate, for a particular time it will be changed because there is a different orientation of or not weight is same. Let's say position or momentum, that overall it will be same, but for a particular instant it will be different, right? Position will be different. They are moving in the room. So now energy will also be changed for particular time, and that energy is E1, overall energy is E1, at particular time that's the microstate. So macro state is that overall system, and under that system, you will have a different orientation like this. Means every time you are starting, let's say t equal to 0, then there will be a different orientation. After t equal to someone, after 1 second, orientation will be different. T equal to 2, orientation will be different. Up to t equals to capital T, you will have infinite number of orientation of this single macro state. Is this clear?
Yes.
This is the each and every orientation is called a microstate. So we will have an enormous number of microstate. Although the
It's
macrostate is
changing in
same,
every second.
huh?
It is changing in every second.
Every second. Obviously, no, molecules are moving. There are 10 to the power 23 molecules. So every second there will be different number of orientation. Different. If you click a picture each and every second, you will see different picture. That's why you
The
will have
time gap is 1 second or smaller than that.
you know, it's actually continuous. That's why I have given the integration sign, right? For an each and
Yes.
every second, it will change. Or you can think like or way smaller than this. It's always changing. So now, if you want to calculate now the energy, then how you can calculate? This is the energy for at instant time t, okay? And after dt time, it's changing. So you have to integrate from 0 to t, and then you have to divide it by total time t. Then obviously we will have the average energy. This is the average energy. This is called time average energy, and that must be equals to E1. That is the way you can calculate the energy of a macroscopic system. Is it clear?
Why it is equal to U1?
Otherwise, how? E1, E1 is what? E1 is the total energy, correct?
E2 is also total energy.
Which which one?
E2.
E2 is a different condition. Then N2, V2, T2 are different. Everything that is a different macro state. So you you can confuse between two different macro state. We are now focusing only this macro state. Under this macro state, these microstates are there. Under this macro state, different microstate will be there. That's a different microstate, now. There's a
The
different
average
thing.
energy is equal with every microstates.
For a particular macrostate, this is a particular macrostate, there will be a different microstate, set of microstates. If you change it, another set of microstate will be generated. If let's say temperature is increased, you are giving some heat, then obviously it moves more faster. So each and every microstate, the energy will be different, and overall the energy is changing. Internal energy will be changed. So you just focus on this. You have only one system. Okay, one macrostate. This is not like E1 is another thing. Each and every second, it's a, let's say it is E0, it's E1, it's E2, E3, and so on, and it's ET. So this is the E for particular second. So, but you are seeing as a whole, so you have to take the average. That's the case, now.
Okay.
Now, if there is doubt, you can ask. Because let's say pressure, if you want to calculate pressure, each and every second pressures are different. But when you calculate a pressure, compute a pressure from outside, that's the average pressure of each and every time. That's the
Average
average.
of the all ensemble.
Not in ensemble, I'm not talking about. All microstate.
Sorry, microstates.
I'm giving you an example. Let's say there is a room. Okay, there is a place, any place. So people are coming, people are going. So in particular, each and every second, the orientation will be changed. Correct?
Yes.
Let's say at t equal to 0, there are 10 people. T equal to 2, after sometimes 12, 8, 9, you will see the change in number. Number will be changed. So now, after a long time, if you average it, then you get a number. Let's say that is 12. So that's 12 is the average number. That you will see from outside. That is the average energy, average number you can see. So that is your E1. And particular time you are getting, that is the E0, E1, E2, E2. These are the microscopic energy of the microstates. When you average out, then the energy you will get, that is the average energy. That you can calculate macroscopically. These things you can calculate. E1, these things you can calculate. When you calculate, this will be E1, and that is not changing.
In a particular time, it can be greater than U1, it can be less than U1,
Yeah,
but the
this
average is 1.
average. Exactly. This ET are varying. So you, when you do, then you, oh, here you will be see like a this kind of distribution. ET is varying from t equal to, let's say, 0 to t. If you average these things, then you will have the E1. That's the meaning of average. That is the average. And that average is important for us people, macroscopic people. Boltzmann was Boltzmann gave this concept. But problem is how you can calculate this. This is not possible to calculate. If you have to calculate the energy for particular instant, and then you have to integrate, then you can calculate only the average. That is not possible. That was not possible. Then gives the idea of ensemble. Gibbs says that, okay, let's say we are not changing time. Time is fixed. Time is not changing, but at a particular time, let's say t equals to t prime, for a particular time, there will be only one microstate. It's clear? Microstate will not, at particular time, there will be only one microstate.
Yes.
One orientation. Now Gibbs says that okay, that's true. Now you make an infinite number copy of this orientation. So at a particular time, he is copying like this of that orientation. He's copying. He's copying, but obviously, uh, you are making copy means it's not Xerox. Like you are just copy paste, copy paste. That is not. He is just let's say at t equal to t prime, there are thousand of people. Everybody has told you have to calculate a particular orientation at t equal to t prime. So everybody will have different orientation.
So what is the same thing?
Time is not changing here. At a particular time, you are accounting all possible orientation.
Okay.
Means, let's say, uh, one fly is in the room. Okay, just this is very important to understand. One fly is in the room and fly is moving in the room. Okay, so we lives in this picture eventually. In these pictures we live. So at a particular time, if you focus the position of the fly, it is changing over the time. At a particular time, there is a one position, another position, and this position is changing with time. Is it correct?
Yes.
Okay. So now these things you will get many number of position you will get x1, x2, x3, x4 up to xt. So then you will have this number of information. Now another thing you can think like this: you have a fly at a particular time t, that is a position. At a particular position you will have now you have a snapshot of that position. Now same room you are copying like same room infinite number of rooms, let's say, and in each and every room there is a fly. Now at a particular time, or you are taking a snapshot. So all rooms you are taking a snapshot. So the position will be fly will not be the same.
Yes.
Is it clear? Now you combine those all picture, you will see the same set of pictures will be there because both are infinite. You have infinite number of rooms. All rooms have a fly, and all you have infinite snapshot from all rooms. Other thing is that you have the same room and one fly from 0 to t time. So in every point of this room, you will see the fly. Correct?
Yes.
There will be picture from each and every point of the room. From this picture also, from this picture also.
Both the thing are same.
You see overall, if you collect the all pictures, both set will be the same.
Both will have infinite number
Infinite
possible.
number. This is infinite time. So you will have the fly in each and every corner of the room. So in one photo, the fly will be here, another photo there. So each and every point of the room will
Your
be.
voice was stuck.
Huh?
Your voice was stuck.
Okay, sorry. So I'm saying that each and every point of the room, you will have the fly in this picture because it's flying in the room. Okay.
Yes.
Now in this picture, there are infinite number of rooms. So in my room, the fly is here. Another room flies there. So now also we'll have an infinite number of pictures where the fly is in each point of the room. So same set of pictures you will have in both cases. Is it
Yes.
clear or not?
Yes.
This is the difference. This is the time picture. Time is changing and generating the pictures, and here time is fixed, but you are making the infinite number of copy of that room. That means the macro state, and you are getting the same pictures. So this is called the ensemble picture. This is the
This is
ensemble.
easier than the first case.
This is
Easy than the first case.
you can calculate now. That I will come. If you use this picture, now you can calculate the average. What was average? Here you have to take all E values and then you have to average out. Here also you have to take the all E values from this picture, E1, E2, E3. Then you have to average. That will also be, that average is called ensemble average, and that is denoted like this. This is ensemble average, and that will also be equals to E1. That you can calculate now. If you use this ensemble picture, you can calculate this E1, you can calculate this E2, you can calculate now this daily, and thermodynamically, by experiment also, you can calculate the daily and you can compare whether this is correct or not. Okay. That this is the bridge between statistical thermodynamics. This is how you can, this is statistical mechanics, this distribution. Now by using this distribution, you are calculating the statistical thermodynamical property. So that's why it is statistical thermodynamics. And by in experiment, you can compare the statistical thermodynamics and our traditional thermodynamics results. That's the overall thing. Is it clear or not?
Yes.
So this is brilliance by Gibbs. This idea was provided by Gibbs. This ensemble picture. So there are some assumptions of ensemble picture. These things are taught in class even. So, but let me again re-emphasize. One is these are called postulates. Postulates of this ensemble average. These things are important. One is that, let me read it line by line. Yes. Now I'm saying that this ensemble average and time average will be same.
Yes.
There is no proof. You can feel it, but there is no proof. So that's why this is called this E average, and this is same. This is called ergodic hypothesis. This is hypothesis. This is called ergodic hypothesis.
Now it's clear.
This is ergodic hypothesis. But this is the only option you can do. You can't calculate, never ever calculate this time average. You have to calculate ensemble average. Now, when this ergodic
Yes.
hypothesis will be feasible, first thing, you have to make the really infinite number of copies of this macro state. Then it's feasible, right?
Yes.
If you have only 10 or 20 copies, obviously, then two pictures will not be same. This is the first thing. And this, yes, means ensemble size should be very large. This is one thing. And this time also should be very large. Both should be tends to infinite. As long if it both goes to tends to infinite, then this ergodic hypothesis will be more applicable. That's the thing. Okay. So in our rest of statistical thermodynamics course, you will calculate the various averages using these ensemble pictures. That's the important ensemble. But
Ensemble
how
is
we can
hypothetical.
calculate? How? Repeat. What are you saying?
Ensemble are calculated hypothetically.
Ensemble average? No, you will calculate mathematically.
No, no, the ensemble
Average
particularly one, two.
concept is hypothetical concept, obviously. It is always changing with time. Not there is infinite number of macro state is there. What is saying that at a particular time there is infinite number of macro state you are assuming, so there will be all orientation will be captured. That's the
I am
assumption.
thinking about a particular orientation.
Not particular orientation. The orientation are changing, but not taking the infinite number of copies. It's changing due to changing time.
Yes.
Okay, means when time is varying, this orientation are changing. Let's say this was the macro state, right? This was the macro state, but you will have a collection of macro state. Macro state will be same, obviously. Collection of micro state, because each and every time the orientation will be changed. Let me draw it. This is one orientation. After some time, orientation is different. Here is another orientation. This orientation you will have different number of orientation you will have for different times. because time is changing, so orientation are changing. But overall, these are macrostate is same. Macrostate is N1, V1, and T1. That is not changing. That is same. But orientation are generating due to change in time. But now we are considering in ensemble average, ensemble picture, we are considering, okay, time is fixed, but we are making infinite number of copies of that macro state. So that's why all orientation can be reproduced. Okay,
Okay.
just you can think like that room example, try and that example,
Yes, that is easy.
that because there are lots of particle, try is only one particle.
Is it possible to generate all the microstates?
In which picture, ensemble or time?
Ensemble.
Yes, obviously, then only we
I
can
think time will
calculate
always
the
be greater
average.
than the ensemble.
Otherwise, you can't calculate the average, right?
It is not possible to think about the infinite number of ensembles.
Infinite number of ensemble, obviously, you have to consider. You have to consider. Otherwise, you can't calculate the average.
Okay.
Okay. So this is the ensemble picture. So now now how you can calculate the this E average. Here, statistical mechanics will come. You have to consider the distribution of the energy because this has energy E1, E2, E3. This is changing, right? These things are changing. So you have to calculate this E average. How you can calculate? This you know. Xi, here I equals to 1 to infinity.
Yes.
That's the ensemble average. EI is the energy for each microstate. Macrostate energy is fixed. That is E. Let's say E1 I was considered initially E1. That is not changing. This is changing. Microstate energy is changing. Just only thing is this change is due to uh, different copies. Before it was due to change in time. That is not possible to calculate. But now you can calculate this. Just you have to calculate this expression of pi, and that also you know. Later we will see this you can calculate like this, where this was is the partition function. So essentially average you can
Yes.
calculate. So this is the whole thing. Okay.
Yes.
So here nothing is quantum, everything is classical. You see, when quantum will appear in this distribution, you are considering this is Boltzmann distribution, right? So Boltzmann distribution is classical for classical particle. If this is bosonic particle or fermionic particle, then distribution will be changed. There will be bosonic distribution or fermionic distribution. Then things will be more complicated. Okay, so now you have to study this random variable part because this E is now a random variable, right? E is changing randomly.
Yes.
The random variable part is important. This in chemistry course, basically in BSc or MSc, this random variable part generally don't taught. This is not included in course. Random walk or this stochastic part. These things are not taught, but uh, you can discuss that because so now why that is important. Okay, let's say this is E, right? What is this?
The
This is
average.
this is average. Okay. Now I'm saying this is equals to the this E1 or E, whatever you want to say. This is the actual energy, right? Actual
Yes.
thermodynamical energy, internal energy, that is E, that is equals to E. But this is not changing with time. This is not changing with time. Correct?
Yes.
This is the macroscopic energy. This is not changing with time. Microscopic energies are changing with time. This is fixed. But there will be slight fluctuation. It will be not change very much, obviously, but fluctuation will be there. Correct? That is important. So till now we are talking about the averages. What I have said earlier, that was an incomplete statement, that if you have this kind of system, N1, V1 and T1 or NVT, and if you have the energy E, it will be remain as it is. It's not true actually, completely true. Yes, it will be more or less same, but there will be certain fluctuation around this E. Sometimes value will be less, sometimes value will be. It's not like
Why?
the. It's not like that. Not like microscopic picture. In microscopic microstate, energy is changing drastically. Okay.
Yes.
But here there should be some fluctuation like that. I'm giving example. If you have a glass of water and you are walking, the surface level of water will be fluctuate. Correct?
Yes.
But on an average, the water level will be there, right? On an average, water level will be there, but there will be a fluctuation of that water
If it
level.
is taken for rest for an
Huh?
hour, then it will be steady.
Repeat it.
If it is taken on a rest for 6 or 8 hours or more than 10 hours, it will be
Then also there will be
steady.
fluctuation of that surface level. You can't see it by naked eyes due to air, due to something. Then also there will be some fluctuation. Fluctuation can be very negligible, but obviously there will be a fluctuation. Means if you only want to calculate the average E, let's say it's E, around the E there will be a very, it may be very less fluctuation, it may be very large fluctuation. Fluctuation is, that's why fluctuation is important. How long the fluctuation is, that will uh, guide you. Well, and now you can think as much as it is interacting with the surrounding, the fluctuation will be more.
The system is
Correct?
in equilibrium.
System is equilibrium, but how the equilibrium is obtained? This T. T means what T? What is the T? Temperature, right?
Average temperature.
So if you have a system, you have a, let's say system, it has temperature T. From where this temperature comes? This is the temperature of the surrounding, right? It is equilibrium with
Yes.
that surrounding. Equilibrium with what? It is in equilibrium with the surrounding T. And surrounding temperature is T. That's why it has temperature T. Your room has the same temperature is surrounding when it is in equilibrium. You lock the room and turn on the AC, the equilibrium will be disturbed. It will be not in equilibrium with surrounding right now. Then the temperature will be different. Okay, I'm not saying it is interacting with surrounding, but it's not getting in any heat. Here is the catch. It's interacting with surrounding, but it's not changing its state. It is if heat NVT is there. When the let's say heat is absorbed or heat is going out from the state, then it is called, it will be a new state. Means if you can think like that. Now if the interaction is very less, that is a fluctuation. If the fluctuation is very high, it will be a new state. Okay,
Okay.
clear? Let's say fluctuation is very high, that then that will not be a fluctuation. Fluctuation means that considering mean fixed, there is a fluctuation. This is the fluctuation.
After a certain level, it will be new state.
If the energy exchange is very high, that means uh, if you, let's say I'm calculating, this is capital E, right? It is not the microscopic case. It is not microscopic energy. It's a macroscopic energy. Now you calculate, if you want to calculate the time, it will be like this. Okay. Now how you will draw it? Like this. But it's, there is a fluctuation. Can you see it?
Yes.
That is the fluctuation. It does not mean it's a new state. when it will new state, let's say
Fluctuation is very much high.
like this. This was E1, it is E2. That means some energy gone out. Then it's a new state. It's not fluctuating. It's you can't say this. So how you can draw it? You will draw it like this. It will one thing is that it's not like sorry, fluctuation. At a particular instant, it will change like this. So it is not. You can't say this state and this state is a fluctuating state. It's not. Fluctuation means, but around a particular E value, there is a fluctuation. Here also there is a
Small
fluctuation.
value of change.
Huh. And now fluctuation may be large. You can have a large fluctuation like this. Let's say
Can we calculate the maximum value of fluctuation? After that,
that
it will
will
change the state.
calculate. You don't worry. That will calculate. So as until now we are talking about this average value, right? This was we want to calculate using the ensemble average, right? This is
Yes.
the power of ensemble average. The beauty you can calculate E and also you can calculate the fluctuation of E. That will also calculate this fluctuation of E. So how you
You,
can calculate now this E fluctuation of E these things. Mm, because these things you are calculating fluctuation of E, these things you are calculating from in some microscopic picture. This is a macroscopic things. But how you can calculate these from a microscopic picture where you have to take E1, E2, E3, these things, right? Microscopic energies. So you have this ensemble of this energy. So when you from these energies, ensemble energies, you can have the average energy and you can also have the fluctuation in that energy. Okay, both you can calculate. So how you can calculate? For that you have to study this random walk form or random variable problem because E is now a random variable. So, from if you have a random variable and if you know the distribution of that random variable, you can calculate the E average and fluctuation. These things you can calculate. Okay, is it clear now?
yes.
So entire statistical mechanics is basically based on two things. One is average, another one is fluctuation. Average and fluctuation. Everything is that. In statistical thermodynamics, we generally calculate with this average. Later, you will see fluctuation is also important because these fluctuations are basically giving you the physical properties like heat capacity, like various thermoelectric response. These response functions can be calculated from this fluctuation. So fluctuation is very important. You will see, you will see later. Uh, if possible, I'll say in this fluctuation when you calculate, it will come like 1 by n, where n is the number of particles. So if you have 10 to the power 23 particles, you can see fluctuation will be more or less
1
zero.
by n.
1 by 10 to the power 23. So fluctuation you can see there will be no fluctuation almost.
Yes.
Internal energy, let's say 2 kilocalorie or 3 kilocalorie. Around that, fluctuation is 10 to the power minus 23 kilocalorie. So fluctuation will be zero. So, but when the number is less, then the fluctuation is important. Means if this macro state is not built with 10 to the power 23 molecules instead of 100 molecules, then the fluctuation is important. Okay. That's why in our real life, we can't experience fluctuation. You are saying that the energy will be as it is. Yes, because it's a real life. Because
Yes.
there is a 10 to the power 23 number of molecules. How you can think like that? I gave you na those example of number of people is coming and going.
Yes.
Yeah. Now let's say there is a 10,000 people are coming and going in a let's say you are calculating in a station. In a station area, you will see the average will be more or less same. The average is 12 and you will have the values around that 12 always. So fluctuation is less. But in a lonely place, if you want to calculate, then you will see the fluctuation will be high. Can you
Yes.
get this? That's the case. Just I'm saying this example. Let's say there is a very crowded area and you choose a particular point. You are looking at it, the number of people at that point. So that average you can calculate. Let's say average is 10,000, and at a particular time you will what we will have. It's not the 10,000, around 10,000. That's why you are taking the average, right? So those what are those values? That's are these values. Right? This is the microscopic values. That will be, let's say, 9,999, 10,011, something like that. So fluctuation will be very less. Maybe it's 20 plus 20 or minus 20. But if it is a lonely place, there is only 50 people, then the fluctuation will be plus 5 or minus 5. So that plus 5 and minus 5 is huge fluctuation because the average is 40 only.
Yes.
You get it? So generally you have to calculate the relative fluctuation by mean. That is the important thing. That that part we'll discuss right now. How you can calculate this mean fluctuation, these things. Mean, variance, and standard deviation. Here the um, statistical mechanics is appearing now. By using this, you will later calculate the thermodynamical property that is the statistical thermodynamics. I think this is now clear.
Yes.
I also first time discussing this whole thing as a whole. Separately, I have also discussed, but it's very new thing for me as well. Discussing whole picture. In general, we discuss the ensemble picture differently and this random variable picture differently. But that is there is a bridge. And let me check whether my recording is going on or not. Then everything will be showing me this. Okay. So if you have a doubt, you can ask me. I'm just taking test, then we will then start. Okay, it disconnected. It disconnected. Let me reconnect it. Okay. Now we will discuss this mean, variance, and standard deviation. So we are taking E, right? This is E is now random variable. Random variable, you know?
No.
So you should say it like earlier, and I'm saying random variable. Random means what? It's random. You can take
Changing
any value.
randomly.
There is no bias. There is no bias that it should be like this or positive, negative. This coming like, let's say, random from the random walk. Let's say there is a drunk person. He is coming out of bar and he has a two path. You can go left or you can go right. So he's a drunk person. So he has no bias. He don't know where to go. So he will have a random walk. Let's say first he goes one step forward, then one step backward, one step again backward, one step again forward, like this. So this is called random walk. Okay. Now after some time,
Unbiased.
huh?
Unbiased walk.
Unbiased, totally random. Or in sophisticated language, it is called stochastic. This term you have probably heard, stochastic thermodynamics.
Yes.
That's mean random. Means this very essentially you are studying the stochastic thermodynamics here also because E is random here. E is random. So now when the so essentially if you now if you want to calculate the for this random walk, I'm not going into details. These random walk things. This is a very long discussion. We can have it. There is a random walk problem. There is a different distribution you can have. So when this is happening, there is a probability of having a positive step. There is a distribution of having a negative step. So from that distribution, so for each type of problem, there will be different distribution because let's okay, let me summarize. So when you have this random variable, so now from this random variable, if you want to calculate the average of this random variable, how you will calculate? This formula is always same. EI times PI.
PI.
This is called probability distribution, right? Probability
Yes.
distribution function, or in short, we call it PDF. So this is different for different cases. So random walk, you will have a different type of probability distribution function. For in thermodynamic case, basically we are talking about for that problem, there is a another type of distribution is there, molecular distribution. Molecules are moving, so that is a different distribution. In Maxwell distribution, that's a different type of distribution. These things are different. Formula will be same. We will have just different distribution function that you have to take into care. Now there will be a excellent thing is there. I will coming into that. Okay. So this is E, correct? Average is clear, or I have to give some example how this appears, how you can have it. Do you know how
Give
to
an
do?
example, please.
Okay. Let's say uh, a batsman, any batsman, make 0 run in 10 innings, 5 run in 20 innings, 30 run in 40 innings, 40 run in again 10 innings, and 50 runs in 0 innings. Just like that. Now, if you want to calculate the average run, then how you can calculate average run?
Total run by total innings.
So total run means first is for how in mathematical. That's correct. That's correct. But that is not
10 into 0 plus 20 into 5 plus 40 into 30 plus 10 into 40
let's
plus
say
0
this
into
is
50.
run one. This is run two, run three, run four, run five. Clear? Or you
Yes.
can think you can think like weight in terms of weight. Let me clear it because runs can be anything. Let's say you have 10 people of having 2 kilogram weight and five and here is also two like this. So if you want to calculate the average weight, how you can calculate? This is weight one, correct? In let me
Into
do it.
number of population.
2 into 10, right? Plus 5 into
Yes.
20 plus 30 into 14 plus 40 into 10 plus 50 into 2, correct? And divided by
Summation W.
total population. Let me do it 10, then it will be easier for easy to divide. Then it will be 10 plus 20 plus 40 plus 10 plus 10, right? So it is 90. Clear?
Visible.
Is it clear? So how you can write it? 2 into 10 by 90 plus 5 into 20 by 90 plus 30 into 40 by 90, 40 into 10 by 90 and 50 into 10 by 90. It's clear?
Yes.
So what is that? This is W1, correct? 2 is W1
Yes.
and it is probability of W1.
Yes.
10 by 90 is probability of W1 because 10 people have weight W1 and total is 90 people. So this is 10 by 90 is the probability of having W1 plus W2 into probability of W2 and so on. So essentially we will have sum over Wi, probability of Wi from I1 to 5. The same formula. So generally it should be written as, okay, let me write this probability of EI. In short we write is EI. That's it. So is this clear?
Yes. It's
How
like
this
normal average.
this is
I
the
think it's
normal average
different.
or mean. In statistical way we say mean. Okay. Same thing. It's just a language. It's now this is mean. What is this?
Square mean.
Yes. So how you can calculate? E squared and probability of EI. Same thing.
Yeah.
For this distribution, what will be the mean? If you want to calculate, let's say, for this distribution, you can calculate the mean. It will be 20 plus 100 plus 1200 plus 400 plus 500 divided by 90. Make it 100. Then it will be easier. So it is 12. Just to calculate it, what will be this?
22.22.
22.2, right?
Yes. 22.2.
So this is the mean. So now if you want to calculate the square average, so what will it be? How you can calculate it? It will be just you have to follow this formula. It will be now Wi square P of Wi. This P of Wi will not change, so it will be Wi was first it's 4, so it 2 it will be now 4 into P of Wi, that is 1 by 10, then plus it will be now 25 and the probability is 1 by 5 plus it is now 900, probability is 2 by 5 plus it is 1600, probability is 1 by 10 and later one is uh, 50. So 50 is 2500 1 by 10. So it is just calculate it. What is this? The value. This will be the value, right?
Yes.
So you can see it's huge. Just calculate it. How much it is.
775.4.
So this is our square average. So it is not the same with the E average. E average square and E square average are different. This is our E average.
Yes.
So what will be the E average square? It is just
400.4.
but you see it's very, so why it is important, where it is important. So you see it's e square, so means the larger value will be more dominating now. Clear? Here, these values, when you make it square, this value will be more dominating. So that means if you have the deviation from the mean, here the mean is 20, right? It means 2, 5, 30, 40, and 50. These are the ranks, weights, but the mean weight is 20. So when you deviate from this mean weight, as much as you deviate from the mean weight, maybe less or maybe more, it will affect it here. Okay. So that means
Okay.
this difference between E square average and E average square is essentially signifies the deviation around the mean. It essentially signifies the deviation around the mean. You can take another example. As long as the deviation is, if deviation is high, let's say make its mean is 20, but just take another set where the mean will be 20, but it's hugely less deviated, let's say 15, 18, 20, 22, 23, like that. So that mean is 20, but you see deviation is less. Then you can calculate, you will see the mean will be same, but this value will also will be less because the deviation is less. As long deviation is important, if deviation is increasing, E square average will be increased. Is it clear? Is it clear or not?
Yes.
Okay. So essentially you can say it's proportional to deviation around the mean. And this is called variance. Variance of E. Okay? Variance of E. Now there is another term. You see, this is a huge value. This 700. This is huge value. If you minus it, then it will be around 335, right? 375. Here it is around 375. Okay, but it is squared in unit sense. It's squared, square of E average square. So just if you take a root of variance of E, then it will be around, you see again, 19. Correct?
Yes.
So now this is called, it is not the same unit of
Standard
E, right?
deviation.
It is called standard deviation. Okay, so you see it is coming around 19 and it's correct. You see the deviation is huge. 20, here it is 2, deviation is 18. 5, deviation is 50, deviation 10, deviation 20, deviation 30. So standard deviation means average of deviation. You are doing that only. That you can see here. Uh, it's basically it's why it is around the deviation around the mean that you can see. Just let me do it. So that's why its standard deviation is huge here. So mean value is 20 and deviation is also around 20. So you can see the deviation is very comparable with the mean. And this deviation is called, standard deviation in statistical sense is called fluctuation. Okay, this is the fluctuation. Fluctuating around the mean value. So here fluctuation is very high. Clear?
Yes.
Okay. Now you see variance we have defined like E square average minus E average square, right? So you can calculate it like that. This is also you can calculate like uh, E square minus E average square average. This is this. You can write it like this as well. How? Just do it. Just do it. It is, you see, what is this? This is just deviation from the mean, right?
What?
This is deviation from the mean,
Yes.
and square it and then average it. That is also same with this variance. Just see, it is just e square minus e average square plus minus 2e average. And then again I have to take average. So it is e square average plus e average square minus 2e average, again e average. So essentially it is square average minus e average square. Clear? So it is variance. So that's why variance is actually uh, proportional to our deviation from the mean, but it is square. So in case of standard deviation, you are taking just root. That's why it is the square term will not be there. That's why the standard deviation is directly indicating the deviation around the mean. That is the fluctuation.
What is the
Okay,
original deviation?
original
Deviation?
original deviation is e minus daily, but you have to take the average because e is a variable, right? E is not a fixed value, so you have to
Yes.
take average. So this is the original deviation around the mean. This is the this is actually not important. Why? Because it can cancel out. Positive and negative both can be na.
Yes.
So that will cancel and you can have very less value, although there is a huge deviation. Consider 20 is the mean value. You having value 0, 5, let's say 0, 10, 30, and 40. Then you will have E minus daily, this average is 0, correct?
Yes.
But deviation, huge deviation is there, correct? So that's why
Yes.
it should be, you should consider the square and then average. That is the variance, and then take the square root. That essentially give you the right information about the fluctuation.
It will be a low value.
Why?
Standard deviation
Low value compared to what?
compared to normal deviation.
No, no, no. Normal deviation means you are saying E minus E average.
Yes.
No, E minus E average, but when you take the average, it does not make any sense actually. This does not make any sense. It will give you 0. Is it really 0?
No.
Deviation is really 0. Why it is happening? Because this positive and negative. Mhm. Because this will come positive and this will negative. What you can do? Yes. What you can do? These things. Take mode and then average. That makes sense. That essentially makes the deviation. That makes sense. And that will be equals to the standard deviation sigma. Okay. Is it clear?
Okay. Okay.
Now this is the standard deviation part. Okay. One. Yes. Now we'll have some different distribution that we can have. We can discuss. Okay. Just give me a minute. I'm from toilet. 1 minute. So this part is clear, right? Now we'll see some distribution. Okay. Okay, is this visible? Is that
Yes.
so in general, these random variables are denoted by n. Here I'm discussing as e, but in general you will see it is denoted by n. So what we have now? N is actually sum over I uh, or n p of n. N is varying 0 to n. This is the general definition of average. Okay. N is we are considering n as a random variable. Then it's clear. You can write it
Yes.
if n is random variable. N and probability of n, as we know, nothing is there. So this is the n. Now in general we can write nk, that is also this. This also we have discussed. Okay. Square tree we
Voice is
discussed.
very low.
For n, uh, voice is low. 1 minute. Let me again connect my. I just dropped it because it was. Next day I will change this earbud and I will use a wire. वो जो wire वाला आता है ना तार वाला वो use. Now it is clear,
Yes.
but still it's not connected. I can't hear. Let me disconnect it.
Yes.
For different distribution, this PDF will change. This P are the PDF probability distribution function. This you know. So I'm just giving some example. I'm just giving some example. Let's say we are considering this is called binomial distribution. So and this binomial distribution is for example is the random walk. For random walk, the distribution will be the binomial distribution. Or if you have a coin, multiple coin, if you toss it, that example discussed in class as well. Bhagdisa discussed. So in that discussion also, you will see that random tossing problem, random coin toss.
Okay. So for binomial distribution, the probability of n is essentially n c n e to the power n q to the power n minus n, where p is probability of having that incident. Let's say having a toss head and having output as head. That is p, means positive output.
Positive result.
Positive result. I'm not getting into detail. You can, if you want, I'll share a PDF that it's written in detail. And Q is negative result, right? Negative result means it's 1 minus P. Probability of having
Yes.
negative is 1 minus P. So this distribution is called binomial distribution. So if you calculate for binomial distribution, you can calculate this mean, variance, everything you can calculate. Because now you know what will be now n. N will be sum over n 0 to capital N. It is n into Pn, and Pn is ncn p to the power n, q to the power n minus n. Okay, so this is our n average. So we can calculate n average. So what will be the value of n average? If you calculate, it will be n times p. It's just a binomial distribution. You have studied in class 12 how to calculate this binomial series value of
Yes.
x. So it will be n times p. I'm not going details. I'm just giving you the flavor. Just if you want to calculate the n square, actually these things are calculated by using a generating function. If you have a distribution, these things I want to say, but I don't know whether that is compatible for this course or not. When you have a random variable, like this is n is a random variable. So for for any random variable, there is a distribution. That's true. But in calculating n or the square or nk, these things are not very easy to calculate. It's not very straightforward. For binomial distribution, it's easy. You know the binomial thing, but there are another distribution, like there will be geometric distribution, scalar distribution, Poisson distribution. These distributions are there. For all distribution, it's not very trivial.
Called generating function. And from this generating function, you can calculate the all uh, averages. Okay, but I'm not going into detail. If you want, you can say, then I will go into detail next class. Because today I don't have that much time as well, because it will take a time. So it will be now
Sometimes voice is so low.
sometimes voice is so low because my headphone is disturbing. Then you figure out and say me, and I will correct it. I don't have to do anything. From next class, I will connect that big headphone, and probably the voice will be correct. Okay. Now it is clear, or
Low sound is coming.
low sound is coming. But now headphone is. Let me check if that.
Now it's okay.
Now it's okay, right?
Yes.
Okay. So this is the n square average. If you calculate the n square average, then uh, it will be, if you calculate, it will be n square p square plus np minus np square. Okay. So what will be the variance?
N square minus n average square.
So it will be np minus np square.
Yes.
So if you take np common, then it will be this. Essentially, that is q.
Yes.
So what will be our? Uh, this is important. This is called. Oh, this is a standard deviation. This is root over variance, so it will be npq. But I said you the relative standard deviation is important. That means this, correct?
Yes.
And also standard deviation is denoted like this as well, because it's essentially indicating the fluctuation, right? As I have discussed. So that's why it's also discussed like written like this, del n. So don't be confused. It's the same thing. Okay, clear?
Yes.
So it is proportional to 1 by root n. So you see, the fluctuation will be very less fluctuation will be for our
If
binomial
n is
distribution.
greater, then fluctuation is less.
Huh? And you know what is the n? Here it is n, but in our case, n is the infinite event, number of ensemble or number of molecule even you can think. So it is 10 to the
Yes.
power 23 around. So fluctuation is very less. Okay. But in our case, we can't apply this binomial distribution, because binomial distribution is not the correct thing there. Okay, for that we have to use no, for that microcanonical okay, okay, for this canonical or microcanonical ensemble you can eventually use this binomial distribution and you will have the same result. But uh, in black body radiation, you remember black body radiation, we have to there is another example of distribution, that is for geometric distribution. So in geometric distribution, that is I'm just writing example. This is clear, right? Binomial distribution is clear. Random walk or this statistical
Yes.
system, or this is basically called open system. These are example of binomial distribution. Sorry. And there is another kind of distribution called geometric distribution. Okay, this geometric distribution example is black body radiation. So what is the distribution for then Pn will be only changed. Pn is 1 by 1 plus should I write it like this? 1 minute. Okay, no, let me write it like q to the power n times p. This is the p and q, that is there. Same. This is positive outcome, negative outcome. Q to the power n times p. This is the geometric distribution. So if you want to calculate,
What is the P and Q same?
p means positive outcome, probability of having positive outcome. This p and this p are not the same. This is the probability. And this p and q is the having positive outcome and negative outcome.
Okay.
That's means you are, let's say this this is probability of having n number of head. Then the small p is having probability of head, that is half, and this is q having not probability of not having head. These things I will discuss it if you want. I will discuss it. Just one two example, it will be clear to you. So then n average, if you want to calculate, it will be q by p. I'm not calculating. And for n square average, is quite tricky to calculate here. But if you calculate n square average, so it will be 2q square by p square plus q by p. So the variance will be just, you have to it will be 2q square by p square plus qp minus q square by p square. So it is q square by p square plus q by p. So if you take common q by p, it is q by p plus 1. And this q by p is essentially called mu plus 1. Then the our delta n in standard deviation will be root over mu plus 1 times mu. And so our relative standard deviation, that is del n by n average. So that will be, you see, it is actually mu, sorry. It is mu by mu plus 1 divided by mu. So it is mu plus 1 divided by mu. So it is 1 plus 1 by mu. So it is 1 plus p by q. So p by q is always greater than 0. So you see relative fluctuation is always greater than 1. Is it clear?
So del n always greater than n average.
Del n always greater than in average. So you see the fluctuation is greater than the mean value. So here the fluctuation is huge. So in black body radiation, that's why the fluctuation is huge. Because it follows that geometric
Fluctuation is very
distribution.
large.
Hmm. So in that case, you can't neglect the fluctuation.
Yes.
Means you can think like that. N is varying. Let's say this is n average, but the fluctuation is something like huge fluctuation is there.
Yes.
these terms are important actually. Sometimes this is called this uh, in average is called signal. You are measuring now when in experiment you measure, then you are essentially measure the average value. That's why it's called signal, and this is called noise. It's fluctuation, and then essentially it is called signal to noise ratio. Experimental language it is SNR, signal to noise ratio. Same thing, just different name. So you see signal to noise ratio, if it is greater than 1, that means it's a very, very bad result. Okay. So one more distribution that is very interesting. It is not, let me check. Yes. Is binomial. Okay. There is another distribution. I'm just writing. That is called Poisson distribution. Okay. In Poisson distribution, uh, radioactive decay. Radioactive decay, that is an example of Poisson distribution. In Poisson distribution, this probability Pn is actually e to the power mu to the power n divided by n factorial, like this, where mu is essentially the n average. Okay, I'm not going into details in these things. There is an explicit form. Let me write that. That is better to write. That is n factorial by this is actually n minus NCN formula, but still okay. Let me skip it. But there are different distribution. This is another example of Poisson distribution. In Poisson distribution, why Poisson distribution is very important? Uh, because in Poisson distribution, the mean, that is NP, and also variance, that is also NP. Okay, and any other NK greater or equals to 2 is 0. This is the beauty of Poisson distribution. So now if you want to calculate the variance will be n square
N
p square.
square average minus n average square.
So that will be okay. So from here you can calculate the um, relative fluctuation even. Just let me check
N
where
square
the
average is NP, so it should be NP minus n square p square.
okay. Sorry, then it will be n square p square. Let me check 1 minute. Let me check whether that square is there or not. Okay. Variance is NP. Then how it comes? Sorry. I'm doing the wrong thing. Oh, it is NP. Both mean and variance both are NP. So it will be now then just you have to calculate what will be the n square. NP plus n square p square. Then it's correct. So mean and variance both are NP, correct. So if mean and variance both are NP, then obviously sigma will be root over NP. So relative fluctuation sigma by n average, it will be root over NP by NP. So it is 1 by
1 upon root over NP.
So again it's proportional to 1 by n. So only geometric distribution is very pathetic. But in general, there is just one more thing. then I will not discuss anything. It's actually beyond our discussion, but still I wanted to just give you the example because you are studying these things, how you can calculate the average variance, these things, but if you don't know how to calculate, how you have to take the distribution, then it's difficult, right? So that's why it's important. Now, the sigma by n, if you now want to calculate the, yes, one thing that is Gaussian distribution. Gaussian distribution. So in case of Gaussian distribution, you know, it's look like this. This kind of distribution is called Gaussian distribution, but normal distribution. Normal distribution is mathematical, more mathematical term, but both are the same. Okay. So this is the Pn and this is the n. This is called the Gaussian distribution. Gaussian distribution is very important because if you take the all distribution together, let's say there is a infinite number of Poisson distribution, or there are geometric distribution, or there are binomial distribution. In distribution it is, if you take it large number of distribution, then essentially it will merge to uh, Gaussian distribution or normal distribution. So just let me, there are many other distributions, scalar, negative, binomial, lots of distribution are there, but I'm not going into that. I'm just, yes.
All distribution match to Gaussian distribution.
Yes. When there is a infinite number of distribution, just I'm saying that statement. It is also taught in class, which is called central limit theorem.
Yes.
That is the central limit theorem. Everything will be Gaussian. Everything, every distribution will behave like a Gaussian distribution. If you combine all, because each and everything is, let's say you have an infinite, if you have a geometric distribution, but there are different kind of, let's say one, we are taking Pn, right? Let's say P1n, P2n, P3n, different kind of distribution, geometric distribution are there. And if you add it, then the total distribution, that will be always Gaussian. That I'm saying. That is a central limit theorem. Okay. Is it clear? Okay, I'm not going into mathematical derivation. These are statistical things, but this is the uh, because in class central limit theorem was discussed. That's why I thought I should discuss it.
This theorem is useful in this statistical mechanics.
Exactly. That's why everything is Gaussian. That is the reason. Okay.
In this course, it has detailed explanation for this or not?
No, no, no. I don't think so. I don't know what is in next, but as Bagdisa discussed this central limit theorem, I just mentioned there are different distribution, but still, if you have the infinite, not infinite, as long as this number of distribution increase, you are adding, so then it will be eventually converged to Gaussian distribution. That is called normal distribution. That's why non-Gaussian distribution is very much important. Okay, so let me stop here today.
Okay.
Yes, it's already okay. So next class, let's see what we can discuss. Probably in next class we can will be more involved in statistical thermodynamics. Then we will discuss the average property distribution. This thing. Probably today, is it clear that ensemble picture and this original picture, how we can relate with it and how we can calculate the actual thermodynamic values by using this hypothesis, ergodic hypothesis, correct?
Yes.
These things. This is very important. This is the base of the thermodynamic. You have to understand it. There is no other option. Okay, so have you any doubt? So you can ask me. or in regarding this discussion or regarding these uh, lectures of this week. You can also ask me in email or WhatsApp. Okay, my WhatsApp number I'm just giving, so that if you have any doubt regarding this class or regarding this course, anything, you can ask me. This is my WhatsApp number. Okay.
This course is about statistical mechanics or statistical thermodynamics.
It's actually statistical mechanics. All statistical thermodynamics will also be there, and also other quantum dynamics 6 will also be there. Probably, I don't know. I have not seen the total course structure, but it's actually based on statistical mechanics. So statistical thermodynamics will also be a part of statistical mechanics. You see, using the statistical mechanics, you are essentially calculating the proper thermodynamic property. So that's the statistical thermodynamics. It's not very different
Yes,
too. If you want to study statistical thermodynamics, you have to study statistical mechanics. And these things is statistics using random variable. When using the when you apply the statistical property to calculate internal energy average or these things, then it is when you are applying the statistics in the motion of molecules, mechanical motion. It's mechanical motion, right? It's moving, it has energy in these things, then it's statistical mechanics. And by using this, if you want to calculate this in average value, ensemble average value, like internal energy, entropy, enthalpy, these things, it's statistical thermodynamics. It's very equivalent. Statistics is really different. The statistical mechanics and thermodynamics is more or less equivalent.
it is tough than the statistical thermodynamics.
No, it's a core more uh, fundamental. Okay, so let
In
me.
which book these concepts are given?
I don't know. I have studied it in my coursework, PhD coursework, and MSc. Mercury is there, and one book is there, Patria. In that book, it's or you can if you want to
Which
study
book?
the Patria, probably I have to check the name. Or if you want to just learn the thermodynamics, statistical thermodynamics part, Callen is very good. Both normal thermodynamics and statistical for both.
What?
Callen book, Callen. But this
Castellan.
is Callen. Callen is for thermodynamics. Castellan. Callen book is for the statistical thermodynamics and Callen. From but the statistical thermodynamics, statistical mechanics, this part is well written in Mercury and Patria.
Macquarie. Okay, then it's right.
But Mercury is very difficult to read. You can read the Patria or G.S. Agarwal. They
Yes.
have this. Okay. So let me stop sharing. Okay. So if you have any doubt, you can ask. Otherwise, we'll meet again in next week from 4 p.m. Sunday. If you have any doubt, you can send me in WhatsApp or mail. You can mail me. My mail ID is already there.
What was the main outcome from this week?
I don't know. He's just discussing the historical background and formulation. Then probably next week he will. In last lecture he discussed the postulate, right? Then
Yes.
he will go into the ensemble pictures, microthermic. I think. Then probably the average values he will calculate in that way.
Okay. Thank you.
Okay. Okay. So again, we'll meet in next class.